This is geometry lesson 5.4, proofs using transitivity. Your big idea says one way of proving two things equal or congruent is to show that the things are both equal or congruent to the same thing. So we're using the transitive property to prove that things are congruent to each other. So we're going to talk a little bit here about some formal proofs, what they look like, what has to be in it. And then we're going to use our transitive property to look at some new ways at characterizing things, angles specifically, from those figures we've looked at where there's parallel lines being cut by a transversal. All right, so let's start with proofs. So a typical proof in geometry, you've got your PQ statement. If this is true, then this is true. Okay, and we're trying to prove that. And so we have a given and a proof. Something's always given to us, and we're always trying to prove something. That's kind of the whole point. And so those are your P's and your Q's. Whatever you're given is P. So if this is true, go ahead and show me that this is also true. Prove this. And those are always the first and the last line of whatever your proof is. The third thing, so here's one, here's two. The third thing that should be given in a proof is some kind of drawing. Here in geometry, we're looking at something, some kind of figure, prove it to be true. We need to see what's going on. So there's your drawing. And then the fourth component is just the actual proof itself. Everything that's in between, you're given in your proof. All of your statements that get you from A to B or from P to Q in this case. All right, so proof is a logical argument. We have conclusions and justifications. So we're allowed to conclude this, here's why. We're allowed to conclude this, here's why. And then Q is shown to follow from P. We start with P and we eventually get to Q through all of these conclusions and justifications. We number the steps in the proof so that we can connect the conclusions to the justifications and we know which one matches which. So below you've got a beautiful proof. Everybody loves these so much. But once you kind of get the hang of them and you can see them, they're sometimes very difficult to come up with on your own when you have to fill in everything in a proof. But when you see it laid out in front of you, it does make a lot of sense. Okay, so we're going to start here with what's given to us. You can see the picture, and then the given kind of describes what's in the picture. So we have circle A. So first of all, circles are always named by their center. So that's why this is called circle A, with radius AB. Now we've got two circles here clearly, and they're overlapping. And so there's kind of a lot going on, but if you do notice the outside of circle A, I'll go ahead and highlight it in blue here. That's circle A. And what looks to be the bottom of that triangle from center to the outside is AB. That's the radius of the circle. It goes from the center to the outside. And we know that the radius is the same in every single direction. Then we also have circle B. We'll highlight that here in red. Again, it's called circle B because the center is point B. And it has radius BA from the center to the outside of that circle. So notice AB and BA, the bottom of that triangle is also the radius of circle A. It's also the radius of circle B. And then we've looked at this stuff before. Let's bring it back. We're relating circle A and circle B. Okay, this is the intersection. So just what do they share? They only share points C and point D. Okay, we're not counting the inside of these circles, just the outer edge. What is common between these two circles? The only places that they cross is point C and point D. That's what this is saying right here. So given all of this, we're going to prove that this triangle we see here in the middle is an equilateral triangle. So before we go through the proof, let's talk about why that's true, because you got to know where you're going if you're going to make a proof here. So we just talked about how circle A, the radius is AB, and then circle B has the same radius. So each one of those circles is the same size. We know that because the radius is the same in both circles. Okay. Now, we've also got these other lines drawn, which looks like a triangle, but if we again look at those sides closely, they're going from the center of the circle to the outside. Okay, we could draw it from A to D and it would be the same there as well. The reason I know that is because that's the definition of a circle. The distance from the center to the outside in any direction is called the radius, and it's equal everywhere we go. So from A to C is going to be the same as from A to B because both of those represent the radius of circle A. If you look at circle B, we obviously know we've got AB right here. It's going to match BC because those are both the radius to this circle. B to A, center to outside, B to C, center to outside. So those have to be equal to each other. And since both circles are using AB as their radius, we know that all of these lines are equal. So how do we put that all in a proof, though, to prove that this is an equilateral triangle? All three of those sides are the same length. All right, you always start a proof with a given. Notice I've got all my conclusions numbered and then my justifications. We're going to talk about how we can actually cut down a little bit on these justifications. You can see what's in parentheses. That's really all that's necessary. But I do like that it kind of explains why they're giving that as the justification. So we'll take a look at that. Some people like to just put all of the given right up front, just get it out of the way, and that's fine. You could totally put all of this in there. If you kind of scan through it, you'll notice they actually never use this as part of the given. The fact that these cross at C and D never has to be stated here because it doesn't help us prove that this is equilateral. Okay, but it is important to know as we're looking at this. The only things that we're stating here as givens is that we have these two circles. The reason we have to state that is at some point we're going to say, I know these two lines are equal because they're part of a circle. Well, before I can start saying, well, the definition of a circle says this, I have to state that there actually is a circle in the problem. And that's where people really start to dislike proofs, is because it's like, well, why do I have to state that it's a circle? We all know it's a circle. And that's kind of the nitty gritty of proofs. You have to put everything out there. You have to state everything that you're given, and then you can start saying, well, I know this is true because I already have this. So it can be a little tedious, and that's why people don't like proofs. But when we look at this, we're stating the fact that we have circles. You could put those both up front if you want. We already talked about this. AC is going to equal AB because each one of those is the radius of a circle. So it says all the points of a circle are equidistant from the center of the circle. Okay, like we said, the outside of the circle to the center is the same in every direction. Therefore, we know AC is equal to AB. Now, you wouldn't have to write out this sentence like this. You could just put this fact right here. The reason I know that this equals this equals this, is because it's the radius of the circle. It's the definition of what a circle is. Okay, next line, they're going to go talk about circle B, and now they're going to say that AB equals BC. So I know that this one equals this one. And again, the reason I know that is because each one of those lines represents the distance from the center of the circle to the outside. So clearly they're equal based on the definition of a circle. So for 2 and 4, you literally could just write definition of a circle. That would be perfectly acceptable. And now, based on our transitive property, which we know a lot now, we've used it a ton, we know that AC equals BC. Going back to this, now we already knew that just through reasoning, but how do we put it in a proof? Okay, to prove it, you got to have evidence. So AC equals AB, AB equals BC. You notice that AB shows up twice. So if this is equal to AB and this is equal to AB, they are equal to each other. That's your transitive property. And once we've now stated that all of these are equal to each other, well, now we know we have an equilateral triangle because that's the definition of what an equilateral triangle is. They wrote it out. They said the measure of all the sides of the triangle are equal, therefore we know the triangle is equivalent. You could just write that out, or you could just write this the definition of what an equilateral triangle is. All right, so there's a quick look at what a good formal proof looks like. Let's get this back in focus for you. So again, 4 things in a proof: the given and what you're trying to prove, some kind of drawing, and then the proof itself, which is all of these conclusions and justifications that get you from P to Q. All right. Now, we're going to kind of use that same logic of thinking. We're using the transitive property to prove things, but now we're going to kind of change pace. We're going to go back to looking at lines that are crossed with the transversal. We're going to look at parallel ones. Right here, the ones that were given in this picture are not parallel clearly. but they can still tell us the different kinds of angles that we've got. So we know we have vertical angles and we have corresponding angles. Now, if these are not parallel, corresponding angles are not equal. It's only when those lines are parallel. But verticals are always equal to each other. And so we've talked about vertical angles. We've talked about linear pairs. All of these ones next to each other are on a straight line. They're going to add up to 180. Those are linear pairs. And we've talked about the corresponding angles, the ones that match up. 1 and 5, 2 and 6, 4 and 7, 3 and 8. In a picture like this, there's nothing special about them, but they're still called corresponding. They're in the same position. When those lines are parallel, corresponding are equal. So we're going to use the transitive property to go ahead and come up with some new pairs of angles. And we'll get to that in just a second. First thing we want to talk about here are the difference between interior and exterior. Should make a lot of sense. You've got these two lines. Everything here between them, all of those angles, so 4, 3, 5, 6, those are called interior angles because they're inside those two lines. Makes sense. Exterior angles are going to be on the outside. Everything out here. So 1 and 2 and 7 and 8. Those are your interior and your exterior. Now, one other piece of classification that we're going to look at is we're going to look at same side and we're going to look at alternate. And so that's talking about the transversal. So of the transversal. So 3 and 6 are on the same side. 4 and 6 are alternate. One's on the left of the transversal and one's on the right. We have alternates here as well. And so we're going to specifically look at angles that are equal to each other. We're going to look at 4 and 6 being equal. We know that right away. Now these lines aren't parallel, but when the lines are parallel, they'll be equal because 6 corresponds to 2 and then 2 is vertical to 4. All right, let's take a look on the other side with actual parallel lines. So before we get to this parallel lines theorem, let's talk about what we know. If these lines are parallel, we knew that 6 matched 2 because they're corresponding. So angle 6 equals angle 2. Do like a little mini proof here. We knew that was true because they're corresponding. We also knew, let's use blue here, that 2 equals 4 because they're vertical. And so we knew that, okay, 6 was equal to 2, 2 is equal to 4. So that means all of these are going to be equal to each other. So angle 6 actually equals angle 4. But why is that true? Take a look. That's what we're talking about here in this unit. Using the transitive property to prove things. 6 is equal to 2. 4 is equal to 2. So therefore, I know angle 6 equals angle 4. And that's the transitive property. Okay, so if angle 6 equals angle 4, we no longer have to make all these jumps and go corresponding to vertical. We can relate these directly to each other right off the bat. Take a look at what these are. They're on the inside, and they're on opposite sides of the transversal. Okay, these are called alternate interior angles. Alternate, again, being on opposite sides of the transversal. Interior meaning being between the parallel lines. So we can just now go straight to this. Alternate interior angles are always congruent. Instead of talking about correspondings and verticals, we can kind of skip that because of the transitive property and now directly relate alternate interior angles. So because of that, I can say 6 equals 4. I can also say 3 equals 5. Those are alternate interior angles. They're on opposite sides of the transversal, and they're in between parallel lines. Now, 5 and 3, you can look. Those are big, obtuse angles. 4 and 6, those are small, acute angles. So they're not all equal to each other, but 4 and 6 equal each other, and 3 and 5 equal each other. The same is going to hold true for alternate exterior. So here's your transversal. Here's 8 and 1. Those would be alternate exterior because they're on the outside of the parallel lines. That's the exterior, and they're on opposite left and right of the transversal. So why are these equal to each other? If we go back to correspondings and verticals, 8 corresponds to 3. 3 is vertical to 1. So since 8 is equal to 3 and 1 is equal to 3, 8 and 1 are equal to each other. Okay, so alternate exterior angles are always going to be equal. So 8 equals 1, and the other ones are also equal. 7 equals 2. Okay, and then the last piece here, same side interior. So same side, they're both on the right of the transversal or they're both on the left of the transversal. Talking specifically about interiors here, they're always going to be supplementary. So we've gone through these and shown that these angles get spread out throughout the whole thing. So like for instance, if 3 is 120, so is this one, so is this one, so is this one. And then the other angle is always going to be supplementary to it because we've got linear pairs all over this. So this has to be 60, corresponding is 60, vertical is 60, vertical is 60, or corresponding. So if you look at the same side interior now and just directly relate those, 3 to 6, they're always going to add up to 180. Look at these two, same side interior. 4 and 5 are always going to add up to 180. They're always going to be supplementary. So make sure you know supplementary is 180. And so same side interior angles, we're always allowed to assume that they add up to 180 now based on this theorem. We got all of this proven through our transitive property. So we're talking about angle 3 plus angle 6. They're always going to equal 180. And then my other same side interior, angle 4 and angle 5. Same side interior in between the parallel lines, same side of the transversal, always going to add up to 180. Now we're not covering it here, but if you do take a look, what about same side exterior? 1 and 7 add up to 180. 2 and 8 add up to 180. So same side exterior are also supplementary. All right, real quick now to finish this off. We got example number 1. It's done for you. Just want to take a look at it. So pretend the solution wasn't there in front of you. It says these lines are parallel. We need to know that to assume things are equal. If measure of angle 3 is 38, find 1 and find 2. So I can say that 3 and 2 are equal. And the reason is those are alternate interior angles. So angles 2 and 3 are alternate interior. Okay, therefore they're equal to each other. Therefore, both of them are 38. And angles 1 and 2, they're a linear pair. Right? These add up to 180 because together they're forming a straight line. Half a circle around their intersection as the center of that circle. That's 180 degrees. And so I know this is 142. I would take 138 away from 180, which they're showing right here. And so if you are given just one angle in this picture, you can fill it all in. And now we don't have to go from corresponding to verticals. We can go directly to alternate interiors and linear pairs. All right, to wrap this up now, everything we talked about up here was when you were given parallel lines. Then you're allowed to assume things are equal. Well, the opposite is true. If I see this type of picture and I'm wondering if those are parallel, but it's not given to me, but I see angles equal in the correct spots, then I am allowed to assume that they're parallel. So going the other direction now, your alternate interior angles theorem. If two lines are cut by a transversal and I see alternate interior angles are congruent, so if I see equal alternate interiors, then I know those two lines are parallel. So it goes both directions. If I see parallel first, I know alternate interiors are equal. Or if I see alternate interior angles being equal, then I know those lines are parallel. So it's just telling you basically that you can go both ways here. Same thing for alternate exterior. All right, if alternate exterior are congruent, I know the lines are parallel. Same thing with same side interiors. If I see two lines being cut by a transversal and the same side interiors are adding up to 180, I know that they're parallel. All right, so that's what that says there. And it all gets wrapped up here at the bottom. So here's when you're starting with parallel lines, you know corresponding angles are congruent. Same thing with alternate interior, alternate exterior, and my same sides are supplementary. And if you forget that, it's kind of easy. It's all S's. Same sides are supplementary. And then if I'm going the other way, I need to prove that the lines are parallel. Well, take a look. Are corresponding angles equal? Yes, then I can prove they're parallel. Are alternate interior angles theorem? Yes, then I can prove that they're parallel. Same thing with alternate exterior. And are my same side interior S, 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 are they supplementary? If I see supplementary same sides, then I can prove that these are parallel using these theorems.